Alrighty, you have officially made it to Nuclear Chemistry Part 3, the final video of this selection, and we're going to talk about half-life. Some of this will be familiar to you, so I'm going to go through this fairly fast, pause it as you need it to do the mathematical calculations. And then you can laugh at my joke of the day, the radioactive cat has 18 half-lives, ha ha ha. Okay, so this should be fairly familiar to you. You know that the definition of half-life is the amount of time that it takes for half of the radioactive isotope to decay, meaning that you've got an initial concentration, and for the time for it to take to get to half of that original concentration, that is its half-life. That is the time involved for half of a mass of something to disappear or to decay to something else. That something else we usually designate in the term daughter isotope. The initial or the original thing, we call it the parent isotope, so that's some terminology you need to be aware of. And then these are two formulas that we're going to use consistently. T1 half, or the time the half-life, is equal to 0.693 over K. That should be fairly familiar to you because that is a first order half-life reaction equation. And then you've got this other one which you've used in the past. A mass at time t is equal to A original times E, which is a mathematical function, to the negative KT. So, variables you should know. T1 half is the half-life. Half-life can be measured in seconds, minutes, hours, days, years, light years, whatever you want to do. It's a unit of time. The rate constant is just a constant that I will give you probably in any of these half-life calculations, but you know in kinetics or in the AP exam, if you need to calculate the rate constant, you need to review kinetics in order to do so. The amount at time t, this is the A, and I can ask for the mass at time half-life, or I can ask for the mass at time t, any t that I give you. And I'll also want you to be able to plug into original amounts or original masses into A sub naught. Know that E, which is the opposite of natural log, is just a math function you put in your calculator. It's not an actual variable. And then T is the elapsed time. So I might say 153 seconds has elapsed, or what is the mass at time equals 153 seconds. So it's just a T, and that's going to be mainly solved for in the A equation. All right, let's practice a little bit. So these examples are on your notes. Make sure, and on your problem sets, make sure you do these with me. All right, so we're going to practice some actual calculations with a calculator, and then we're going to practice some estimating so that you can do both based on whether it's given to you on free response or multiple choice. Okay, so first of all, we have given to us thallium-208 undergoes beta decay. We don't really care about any of that. That's just information. It has the half-life of 3.1 minutes. That we need to know. How much time does it take for 1 gram of the isotope to decay to 0.2 grams? So here we go. Here are our givens. The half-life is equal to 3.1 minutes. A naught, the original mass, is 1 gram, using all my sig figs. We now also have the final mass, or AT. I sometimes write A final. And then we want to solve for T, because it says how much time does it take for 1 gram of the isotope to decay to 0.2 grams. So we've got these two equations. We got to figure out which one we need. Maybe we need them both. So since we know both of these equations, we need to plug in our information into one equation and possibly find the information we need for the separate equation. So that's exactly what I'm going to do here. So we need to solve for K first. K in the T1 half is equal to 0.693 over K. And we're actually going to solve for K so that we can use it in the A equation. The AT is equal to A naught e to the negative KT. So let's go ahead and do that first. K is equal to 0.693 divided by 3.1 minutes. All I did was rearrange this equation of a T1 half is equal to 0.693 over K and solve for K. And I get K to be 0.2235 minutes to the negative 1. Okay, or over minutes. So that's K. Now I'm going to plug that in with all my other givens in order to figure out the T involved in this half-life equation. I know that looks a little crowded, but make sure you know that that's the exponent of negative 0.2235 per minute times t. So I need to solve for t. So the way that you do that is by natural logs, which is the opposite of the e function. So you cancel out each of these mathematical functions with each other by multiplying them together. So whatever you do to the left side of the equation, you also do the right side. So make sure you know the basic math of this. So here we go. Let's do natural logs. So the natural log of 0.20 grams is equal to the natural log of 1 times e to the negative 0.002235 over minutes times t. So then we have to simplify. Is equal to this right here, ln of e. Actually, we'll cancel out ln e. That 1 right there is useless because it's just 1. Anything multiplied by 1 is the same. And that actually will bring the exponent down to an original value down here. So we're going to say negative 0.2235 per minute times t. Okay, so at this point, I can actually go ahead and solve for ln of 0.2 grams. And I'm actually going to take that number and divide it by my 0.2235 per minute to solve for t by itself. So taking this number and dividing it on both sides, I'm going to get t is equal to 7.20 minutes. And that is my final answer. So the time it takes for the isotope to decay is 7.20 minutes. Just have to use both equations. You have to know how to use your units appropriately as well as your givens. Okay, part B of this says, how much remains after 23 minutes? So since this is within the same problem, it's talking about the same substance, and it's talking about something with the same half-life and the same original value. So same isotope, same K, same half-life. If you've got information given to you, we're just going to plug it into this equation. A is equal to at the time t is equal to a sub naught 0 e to the negative kt. Plugging in information, we have 11.0 grams initial value, e to the negative k. K was already determined up in the part A, 0.2235 per minute times time elapsed of 23 minutes. So all you do is you put that calculation in your calculator, and whenever you multiply everything out, you should get, for your answer, 0.064 grams. That is the amount at time t, at 23 minutes. All right, so that's a calculator-based one. Let's do one more. If you have 2 grams of a sample of strontium-90, after 2 years, 1.906 grams of the sample remains. What is the half-life of the isotope? So we're also going to use both of these equations. We're going to actually use the A one first to determine K, and then plug K in to the half-life equation. T is equal to T1/2 is equal to 0.693 divided by K. So let's do that. And we're going to plug in the information given to us here. So knowing this, I'm actually going to solve for what I want to solve for first. I'm going to solve for K, variable-wise, and then I'll plug all my information. So it's just a separate way of doing the same thing. So take ln of both sides. Let me actually show you all the calculations here. What I did here, where the star is I went ahead and took my e out of the whole situation, because my ln times that entire variable a naught e to the negative kt means ln of a times the exponent all by itself without the e any longer. And so then over here, I'm dividing by ln of a naught and dividing by ln of a naught on both sides, and actually can combine these two a values in order to get ln as one function. Ln of a t divided by a naught is equal to the variables that were left over here, which is negative kt. So if I want to isolate k all by itself, I'm going to divide by k on both sides and get t is equal to ln at divided by a naught divided by negative, k is equal to negative that over negative t. And so whenever I solve for that, I'm actually just going to plug in the information given to me, and I've got ln of 1.906 grams divided by 2.00 grams. That's the A at time t and the mass at time 0, and then divided by negative 2 years. This right here is just going to be the k value that I need, which is 0.0241 years to the negative 1, or over years. So that k value, I'm now going to plug into t is equal to 1/2, 0.693 over k. Plugging that in, I'm actually going to get my half-life in years now. So 0.693 divided by the number k is going to be 28.8 years. Sorry about the mumble jumble there and the mathematical stuff being thrown around, but just make sure you can solve either way. You can plug in, you can put it in your solve feature of your calculator, or you can solve for variables and then plug in the information at the end. Okay, second part. How many grams of the original sample will remain after exactly 5 years? So we have the original sample, which is given to us initially, and then we're using the same type of half-life equation, and all we need to know is the final mass. So we're going to use the A formula. The initial mass given to us is previously given in the problem as 2 grams. We're using the e to the negative k that we already calculated, 0.024 years to the negative 1, and it says the elapsed time is exactly 5 years. So plug that in your calculator and you get AT is equal to 1.77 grams. And using correct sig figs, I know 5 years it says exactly 5 years. I could say 0.00 to help with my confirmation of sig figs. Okay, so now we have the calculator-based ones down. We need to do the non-calculator-based, which is a multiple choice section question that could be given to you. So half-life problems are mainly in the multiple choice are going to deal with easy calculations, mainly half-lives that are in full integers, or just simple estimates that, there's an A through E answer choice, and one of them is close, and so you can estimate based on what it's going to be between. Okay, so looking at this one, we have 87.5% of a sample of pure iodine that's going to be totally decaying in 24 days. We want to know the half-life of this iodine 131. So if 87.5% has passed or has been decayed and 24 days have passed, all we want to figure out is, of those 24 days, how many of those days make up one half-life? So this is actually really easy. If you initially have 100% of something and it decays, it goes through one half-life, it's going to be decomposing and decaying into half of its original mass, which is 50%. And that means 50% of the entire mass has decayed. And then we take that other 50% that's still there. I'm going to say original. And another half-life has passed. That is now down to 25% of the original mass that you initially have, or that isotope, which means 75% has decayed. Now, we've already gone through one half-life, two half-lives, and third half-life would mean that 25% of the original, half of that decays, so this is original, half of that decays, that means 12.5% of the original still remains, which means 87.5% has decayed. At that point, you need to figure out how many half-lives have passed. 1, 2, 3. 3 half-lives have passed, making this a really simple calculation. At half-lives, 3 half-lives have passed, and that's equal to 24 days. take your 24 divided by 3, which is equal to 8 days. That answer is B. So it's that simple math, simple calculation, simple percentages. You just need to understand what half-life, that term, means and how you would convert the days into half-lives. Next one, I'm going to let you calculate. You need to make sure that you talk about the fact that you've got 80% of the sample that has decayed, which that is between 2 and 3 half-lives based on your previous problem. You can use that knowledge there. And so you need to figure out the best answer for that percentage of decay. So it's going to be between 2 and 3, and given the fact that it's already told you the half-life is 29 years, that's going to be between 58 and 87 years, and the best answer there is obviously D. So you can do the math here, but this is an estimating answer. All right, so you do the math, and you are a superstar. You have officially finished nuclear chemistry, and you can explore more stuff about antimatter. You can explore more about nuclear chemistry. It's a great field, but make sure you ask me questions as you need. All right, thank you.